This lesson we'll be looking at different types of stationary points. Now we've seen already that a stationary point is a point on the curve where the gradient is equal to 0. And on this graph here we've got 3 stationary points marked, but they're each of a different nature. This first point, A, is what we call a local maximum. So we'll label that one a local maximum at the point A there. And you can see a local maximum is defined by the fact that the slope of the curve to the left of the point is increasing, and then the slope of the curve to the right of the point is decreasing. So we've got a local maximum. At the point B here, we've got what we call a local minimum. And you can see that it follows the shape that immediately to the left of the point the slope is decreasing, immediately to the right of the point the slope is increasing, creating a minimum point. This last type of stationary point is what we call a stationary point of inflection. Stationary point of inflection. And you can see that on either side of the point, the gradient will either be increasing on both sides of the point, so that's what we've got in this case here. It's increasing to the left of C, and then to the right of C it's also increasing. But we can also have it so that it would be decreasing on both sides of the point, and that would take the shape of this here in this little summary box. But it's important to note that at that particular point C there, the gradient is 0. So those are the different types of stationary points we can have. Let's jump straight into a question. Find the stationary points and their nature for the function f of x equals 2 plus 3x minus x cubed, and then sketch the graph. Now, the first thing that we need to do, as always with stationary points, is to just solve the derivative equal to 0. So we'll have f dash x equal to 3 minus 3x squared. We know that we've got a stationary point when the derivative is equal to 0, so we can solve 3 minus 3x squared equals 0, giving us 3x squared equal to 3, x squared equal to 1, and that leaves us with x equal to 1 or x equal to minus 1. So we know that we've got a stationary point at x equals 1 and at x equals minus 1. In fact, we should change this to and. Alrighty, now we need to go ahead and find the y coordinates of the stationary points. So we can sub these x values back into our original function. So we've got when x equals 1, we'll have the function equal to 2 plus 3 times 1 minus x squared, it was from memory, minus x cubed. So we'll get minus 1 cubed. So we've got that equal to 5 minus 1, which will give us 4. So we've got a stationary point, so SP at 1, 4, that's one of our stationary points. And then when x equals minus 1, we have f minus 1 equal to 2 plus 3 times minus 1 minus minus 1 cubed. If we solve that, we'll get 2 minus 3 plus 1, which will give us 0. So stationary point at the point minus 1, 0. So we've got 2 stationary points. Now we need to go ahead and determine the nature of these stationary points. And in order to do that, we need to set up a little table. So determine the nature of stationary points. We need to set up a little table similar to these tables that you've got here, because we need to test the slope of the curve prior to the stationary points that we found and after the stationary points that we've found. So let's set up a little table. We'll have x f dash x at the value of the gradient, and then the shape. Now with these tables, we want to choose x points on either side of our stationary point. So for us, we had a stationary point at x equaled -1 and at x equals 1. So we know that the value of the derivative at x equals -1, that was 0. That's what defines a stationary point, and it was 0 when x was 1 as well. And so the gradient, this is the shape component here, the gradient for these stationary points is just 0. So in other words, the slope is 0. What we want to do is choose a point on either side of these stationary points, as in so a point that's smaller than x equals -1 and a point that's bigger than x equals -1 but smaller than 1, and then a point that's bigger than 1, just to give us an idea of what the graph looks like. So let's choose -2. Between -1 and 1, we'll just choose 0, and bigger than 1, why don't we choose 2. Alrighty, if we solve the derivative, so at x equals -2, so in order to get this here, f dash -2 will be equal to 3 minus 3 times -2 squared. So I've just subbed in x equals -2 into our derivative here. So that will give us -9. Now the value of this isn't overly important to us, but it's the fact that it's a negative. So the fact that it's a negative, I'll add in here the derivative at x equals -2 is a negative, which tells us the slope of the graph leading up to this turning point is negative. Let's do the same for this point here that we've chosen. X equals 0, we'll get 3 minus 3 times 0 squared. That will just give us 3. Again, the value isn't overly important, but it's the fact that it's positive, which tells us that the gradient is going to be positive. So you can get a picture of the shape of the graph here. Alrighty, the last one we'll choose is 2. F dash 2 equals 3 minus 3 times 2 squared, which equals -9. So again, negative, which tells us the gradient is decreasing, and we know that that was a stationary point there. So we can actually see the nature of these stationary points here. We can see that the one at x equals -1 is a minimum by the fact that it's decreasing in front or prior to and then increasing after. And we can see that the stationary point at x equals 1 is a maximum by the fact that the gradient's increasing leading up to it, and then afterwards it's decreasing. So that's minimum, maximum. And then let's go back up to here and just make a note that this point here, 1, 4, was the maximum turning point, and this point here is the minimum turning point. Alrighty, so we've nearly got everything we need to sketch this, but the final thing we need is the intercept. So if I take the x-intercept, we just let y equal 0, or in our case, we're given it in function notation, so we're trying to solve f of x equal to 0, so we'll get 2 plus 3x minus x cubed equals 0. Now we could solve this using the factor theorem that we looked at earlier in the year, but I'm happy for you to use your CAS calculator, the solve function, and you'll find that x is equal to 2 and x is equal to -1. So there are two x-intercepts. Find our y-intercept. We solve x equal to 0, so in other words we're solving f of 0. Now we know f of 0 will give us 2 plus 3 times 0 minus 0 cubed. That's just going to give us 2. So we've got a y-intercept at 2 and x-intercept at 2 and -1. Alrighty, so we've got all the information we need to sketch this. Let's go ahead and sketch it. Alrighty, so I've gone ahead and sketched that graph there, labeling the key features. We had a y-intercept at 2, an x-intercept at 2 and -1, and we know that our minimum turning point was at -1, 0, and our maximum turning point was at 1, 4. So you can see how filling out this table helped us with finding the shape of the graph.